All right, we're good. Okay, so I'm going to be talking about one of Witten's paper from I think the 80s, titled "Supersymmetry and Morse Theory." I think this is a fascinating paper. I've been meaning to read for a while, but what better chance than to give a talk about it? I will begin with this disclaimer: is I'm not a physicist, so I have to talk about physics at the beginning. But if there's anything that seems fishy, it's probably going to be my own mistake out of not knowing physics. But yeah, it was a very influential paper, and we're going to be diving into it. So, what is the paper about? What did Witten do that was so influential? Is he used supersymmetry to prove something called the Morse inequalities, which in some way kind of give you some restrictions as a type of. It gives you restrictions on the type of spaces you can have given some Morse function. If you have a function, some special family of function, a special type of function on a space, it gives you, by looking at the critical points, what kind of spaces allow this function to exist. And he did a proof that was using physical arguments. It was not a mathematical proof, and that's what I find fascinating about it. It's one of those rare instances, or rare, it's not that rare, but one of those fun instances where physics just went on and proved an abstract mathematical result. So, okay. So the talk is going to be divided into 3 parts. The first part is going to be on supersymmetry. So I'll do my best to give you a good overview of what supersymmetry is about. And then I'll go on to give you a brief overview of classical Morse theory. So Morse theory has been around for a very long time. This was something that was known for, I think, since around the 50s and 40s, 50s. And what Witten gave us is a whole new perspective on how to think about Morse theory. But I'll do a recap of the classical version of Morse theory that was done before, and then I'll go to the proof, Witten's proof of the Morse inequalities. Okay, so first part, supersymmetry. So what is supersymmetry? What is a supersymmetry theory? More specifically, I'm going to stick to the case of quantum mechanics. This is a theory where you have, I guess, let's start like this. Usually in quantum mechanics, you have your Hilbert space of states, is where your particles live. And we know that we have 2 types of particles. We have bosons, and we have fermions. So these are going to be my bosons. These are going to be my fermions. And my understanding of supersymmetry, again, I'm not a physicist, but it's that you want an operator that allows it to go from one to the other and vice versa. Why would you want this? I am unsure, but physicists want this. So we have this decomposition of our Hilbert space into these 2 families, and something we can do, I guess, just to keep track of where we're working in, is to define this operator. So we're going to define the operator minus 1 to the f, which is going to be given by plus 1 if my state is a boson, and a minus 1 if my state is a fermion. So I just want to have keep track of where my state is, and just extend it linearly over this direct sum. Okay. So this is just in order to do some bookkeeping on what we do things. And again, the goal of supersymmetry is to have an operator that lets us go from one to the other. So what does this mean? And here I'm going to start my definition of supersymmetry theory. A supersymmetry theory of quantum mechanics is the following data. first, as almost everything in quantum mechanics, we need to start with a Hamiltonian. So this is going to be my Hamiltonian. And we want it to be self-adjoint or Hermitian. We want this, and well, I guess I should have also specified we need a Hilbert space to begin with, but let's just fix a Hilbert space, and supersymmetry theory on this Hilbert space is going to be the data of a Hamiltonian, and the following operators, and we're going to be called the operators Q1 up to Qn. These are going to be operators on my Hilbert space called supercharges. Again, we want these to be self-adjoint, and we want these to satisfy some properties. So, like I mentioned, we want to be able to go between our two copies or our two subspaces of our Hilbert space. So, how do we encode that? Such that we have the properties A is that -1 to the f qi plus qi minus 1 to the f. We want this to be equal to 0. This is exactly the information that if I take something in h plus, it's going to send it to h minus. And if I take something from h minus, it's going to send it to h plus. It's encoded into this equation here. It's equivalent to it. Part 2, we want this to be a symmetry. We want the QIs to be a symmetry of our Hamiltonian. So we need the commutator to be equal to 0. So
what is, like, I understand -1 to the f qi. What's qi minus 1 to the f?
QI, so it's a composition of operators. Okay. I'm just composing, yeah. Okay, so this.
So that still has to act on a function.
Yeah,
okay.
Yeah. So I take a psi, I acted by this,
Yeah.
plus or minus,
Yeah.
IQ, and so on.
What's the f?
I have no idea.
That's a good question. What does the f stand for?
Number of fermions? Yeah, I know it has to, like, I know it's related to the Witten index, and I'll talk about that in a bit, but I don't know if the f comes from that, I guess. I'm not sure. That's the index, yeah. But I don't know if the f.
I'm pretty sure it's the number of fermions, but 95% sure.
I am not a physicist, so I will not comment on anything. Okay, but yeah, so this is telling me that I want H to be a symmetry. I want Qi to be a symmetry of my Hamiltonian. And now we come with these other two properties, which are funny. So we want Qi squared to be H for every I. Again, this is all for every I, B, C, D. And we want the anti-commutator of Qi and Qj to vanish. Okay, so I kind of, I guess, lied a little bit on the order of these things, or I guess I kind of did what I thought was the right order in my head, but usually you want to start with these because these are conditions that generate an algebra. So you want to start with these, and this is an extra condition you want on your operators, but this is a result of these two. Okay, so when I was reading the paper, and also if you read I guess the link I have there, I guess I never said it, but the link there on the board is some notes that I wrote, and you can follow along if you want, if you manage to write all that down. But when I was writing notes and I was reading the paper, I have no contact with supersymmetry. This is my first time actually doing supersymmetry or doing anything about supersymmetry. And I wrote the notes from the point of view of someone who's discovering supersymmetry. I look at these rules and I started like, what do they mean? Start doing algebra, start just chugging the math, follow the math, and see what you say about these things. So yeah, let's do that. Like I mentioned, the first one is just telling you that the QIs let you go between the H plus and the H minus. Of course, we want our QIs to be symmetries. Otherwise, why would we call this a supersymmetry? So we want the QIs to be symmetries. And this one I have no idea, other than it being a condition that generates an algebra. I don't really know what it means, like physically, but I can tell you what this one means, because you can do some math and figure it out. So Let's look at corollaries of this, or yeah.
D is meaning they want an
Sorry?
D is anti-commutation relation. You want your charges to anti-commute.
Yeah. So I understand that. I don't know why. Like, why would I want that?
You mean like physics?
Yeah, physically. Consequences, let's call it. Okay, so something we can note is that this condition here forces your H to be positive semi-definite. Because if you do a state psi, you do H, you do psi, you're going to have Qi squared. And now I can, again, these are self-adjoint, so I can move one of the Qi's here. It's going to have a dagger, but it's self-adjoint. It's going to be Qi itself. I'm going to have this other Qi. I'm going to move it here. And this is the norm of Qi psi, norm squared. And this is always bigger than or equal to 0. So my first consequence of this thing is that it forces my H to be positive semi-definite. So that's cool. Now something else you can do is if you take this equation, you multiply by Qi on the right, you're going to have a Qi squared. That's going to be an H. You're going to have a Qi here. Now you can reuse this rule to anti-commute them. And you're going to end up with, so this is 1. The second consequence you get is that the commutator of -1 f and h is 0, which is surely something you want, because you don't want your fermion to just become a boson as time went by. So you want your -1 to the f to be a symmetry as well of your Hamiltonian. So these are good sanity checks you could do. And yeah, so these two conditions, you can also rewrite them more neatly, which is the way it's usually presented as the anti-commutator of Qi and Qj to be equal to 2 delta ijh. This is usually what you find in the literature if you figure around. So if you see it, now you know it's really these two. All right, so that's one of the first things you should do when you're given an algebra. That's one of the first things I did when I saw this algebra. Now, what's the other thing you do when you do quantum mechanics? At least in my main memory of when I took quantum mechanics, is if you give me a Hermitian operator or a self-adjoint operator, the first thing I'll care about is the eigenvalue problem for it. So as good physicists, what should we do is look at the eigenvalue problem of this. For each Qi. Let's just fix one Qi. Let's work it out for it. Now, I have a lot of structure. So the fact that Qi acts on H plus and send it to H minus means I can restrict my Qi to H plus. And it's going to be a map from H plus to H minus, and similarly for the other one. So I can decompose my Qi into two components, the Q plus and the Q minus. And now I've reduced my problem from analyzing a full Hilbert space to analyzing a smaller one. So, and similarly for a state, if you suppose it as a boson and a fermion. So what I'm trying to say with this is the eigenvalue problem, Qi psi equal to lambda psi. This is going to be the same as I'm going to compose my Qi plus so plus and a minus. This has to be equal to lambda again. And if you do some algebra, you put all the pluses on one side, all the minuses on another side, and what you're going to find is that, let me just do the algebra. I already have it written down, so I can just do it. Okay, is it small?
It's good, but try to write bigger.
Try to write it bigger, okay.
I think the other thing is that because they're screened on the smaller screen too.
Oh, I see.
Yeah, I guess it's like double weighty.
I see. Oh, that sucks.
It would look good in the recording though.
Okay, so let me plus, take something in plus and send it to a minus. So this whole thing is in a minus. It's an H minus. This is an H minus. And that's minus lambda minus plus lambda. Oops. So Q minus sends something in minus to a plus. So this whole thing is in H plus. So I have something in H plus equal to something in H minus, but it's a direct sum. So this whole thing's in intersection, but it's a direct sum, so intersection is 0. So this whole thing has to be equal to 0. Each side has to equal to 0. So I have that my eigenvalue problem on the whole Hilbert space is equivalent to 2 smaller eigenvalue problems. Okay, so that's a bit of a reduction we've done. We've took this big problem, slowly simplifying it to something nicer. And now we can start doing more stuff. So let me erase this. Okay, so this is really as much as we can do right now with what we have. So now we need to start doing more things with other operators. So when you're given an operator in quantum mechanics, first thing you do is get that operator. At some point, you're going to get stuck. And what you care about now is, well, how does it behave with the Hamiltonian? Now, what I compared with the energy eigenstates. So again, we know that our QIs commute with H, so they're going to share eigenstates. And just for simplicity, let me write, just because I'm fixing a single one, so let let Q equal to Q plus, just for simplicity. And I'm going to let, so I'm going to show you something. Something you can show is that Q minus is actually the adjoint of Q. This just follows from the fact that Q is self-adjoint, do adjoint on both sides. And from where they act on the direct sum, you're going to find that these have to be the same, just from the fact that QI is self-adjoint. Okay? Have any questions?
I'm just going to ask, is H bidimensional?
The Hilbert space? No, not necessarily. Yeah, no, the case we're going to look at, it is not going to be finite dimensional. So, yeah. For a second, I just kind of like doubted myself. I thought it was going to be finite dimensional for some reason, but no. Okay, so let's write this, and now let's look at how our QIs commute with the Hamiltonian, or behave with the Hamiltonian. So we know that H is QI squared, but QI is Q plus and Q minus, which is going to be Q plus Q dagger, all of this squared. And I know that Q squared and Q dagger squared equal to 0. So if I just expand this, I'm going to have Q dagger plus Q dagger Q. And so something we can get from this is that Q and Q dagger also commute with H. Remember, QI was the one that commuted with H originally. Now from this, if you just put the commutator and use H and put it here, you're going to find that Q and Q dagger also commute with H. It's a bit of a computation. Just plug it, and you're going to find that these extra terms cancel out. So now we know that Q and Q dagger also share eigenstates with H. Okay, that's pretty neat. So let's actually look at an eigenstate. So we're going to let psi be.
Why did it square to 0?
You can show it.
Oh, okay, it's just a computation.
Yeah, it's another computation.
Okay.
But it's actually pretty obvious. No, you don't need to. It's because Q goes from H plus to H minus. And if I do Q again, it's going to send H minus to 0. I need a dagger to bring it back to H plus.
Oh, yes.
Yeah.
Okay.
And same for Q dagger. Yeah.
Sorry, I think you just explained this, but what's the dagger? Why are we?
Oh, that's the star Salah joint. So you can put
Q plus self-adjoint.
No. So the QI, remember the QI was Seval joint? But now when we restrict to subspaces, remember that the Q is a restriction to the plus. So these are not going to be self-adjoint. Yeah. Yeah. Okay. So yeah, that's psi b an energy eigenstate. So an E eigenstate. By this I mean just an energy eigenstate with eigenvalue E. Okay. So we know that this is also going to be an eigenstate of the QIs because H commutes with the QIs, with the Q and Q dagger. So what we have is the following. Okay. So it is an energy eigenstate. Then Q psi and Q dagger psi are E eigenstates. E eigenstates. And we can compute the following. We know that H psi is equal to E psi, just by the fact that it's an energy eigenstate. But this side here is the anti-commutator of Q and Q dagger acted on psi. By this I mean Q dagger, Q dagger plus Q dagger Q. And I can move my E to the bottom. So this is equivalent to Q square root of E, Q dagger square root of E, psi equal to psi. And if I call this A, this is going to be my A dagger. Now what I end up with is that I have two operators, A and A dagger, such that their anti-commutator is the identity. Or, sorry, no. I guess, yeah, no, you would have that. Yeah. It's gonna, if you restrict to an energy eigenspace, it's going to be the identity. And you also have that A squared and A dagger squared are equal to 0. Okay. Are we following along so far? Just been doing quantum mechanics.
I think I mean, check that out. But I'm just wondering about the commutator between Q and Q plus. Did we get that from using the commutators of QI or?
The commutator of Q.
Sorry, the anti-commutator.
Oh, yeah. So this is here. So H is equal to QI squared, which is Q plus. And I know that Q squared is 0. Q dagger squared is 0. So you end up with this. And this thing here is equal to. Yeah. Sorry. Okay. So this algebra here is actually something called, well, it is kind of an algebra of fermionic creation and annihilator operators. So somehow our Q and Q plus are these things that create and annihilate things. But the little thing is I divided by E. So I need E to be non-zero for this to happen. And if E is non-zero, then we get something cool. So something about this algebra is that it has irreducible representation of dimension 2. And so this algebra, this is some algebra. I'm not going to assume that you know this. Algebra has an irreducible representation of dimension 2. So let's fix some basis vectors. One is going to be in the bosons. One is going to be in the fermions for a given eigenstate E, eigenvalue, sorry, E. And then we know that A, B, E is going to be equal to my fermion. And on the other hand, A dagger, B, E is going to be equal to 0. Okay. So what am I trying to say with this? Is that whenever I look at at eigenstate with positive energy, when I look at the eigenvalue problem for positive energy, my states always come in two pairs. I always have a boson and a fermion. It's never one alone for positive energy. And yeah, so they always have to come in pairs when you fix an energy level. And something else is that okay, no. So let's keep it there. That's what happens for positive energy. But I still need to worry about the case where I have zero energy.
William asks the question: A and A dagger are defined everywhere, but only one on the E eigenspace.
Are defined everywhere, but only one on the E eigenspace. Yes.
Well, they're defined energy eigenspaces, right?
I think he's asking why is it one everywhere, not just on the eigenspace?
Okay, here I really mean on the eigenspace. I don't know if it's one everywhere.
Oh, it's only
Yeah. That I don't know. But here I mean really on the E eigenspace. I'm not thinking on the whole of H or H plus or H minus. I'm really fixing on this. Okay. So. Yeah. You have to be a bit more careful if you go, like, because you really need this thing happening here. Yeah. Okay. So, but again, we are really relying on the fact that E is non-zero. All of this, we really need that. So here I'm going to put E 0. On the other hand, let's look at the case where E is equal to 0. And for that, we need to do the following, is that if I do, again, remember that my H is semi-definite. Let's take, let's repeat our computation for positive semi-definiteness, but let's take 2 of the same on each side. So this is going to be omega of the anti-commutator of Q and Q dagger. And if I just expand this and move stuff around, it's going to be the norm of Q dagger omega squared plus the norm of Q omega squared. So in other words, my omega is a ground state for the energy if and only if it is annihilated by both Q and Q dagger. All right. So about energy eigenstates coming in pairs, one boson, one minus, one boson, one fermion. But here I can't really say anything. Like if I take, where does omega even live? Is it a plus? Is it a minus? I don't know, because if I take it, if it's a plus, it's going to be sent to 0, not necessarily a minus, so it could be anywhere. I don't know if it makes sense what I'm trying to say. But yeah, so we don't really know where to even put this omega. Where would it even live? We have no real information, and it might not even, like, at this point, we're not even guaranteed that they come in pairs. We don't really know anything. They could just be a lone omega just lying there on the ground state, and we don't know anything. So that's quite annoying. And so yeah, some buzzwords that physicists use, I guess, is, well, that's not physics words, that's proper math, is, the energy spectrum is almost always degenerate because they always come in pairs, but we might have some non-degeneracy. If non-degeneracy occurs, it has to be in the ground state, in the zero energy level. Okay, and this is where this now physics words come in, is if there are no to the eigenvalue problem qi omega equal to 0, we say that supersymmetry is spontaneously broken.
zero. Is that a full sentence? Okay.
Sorry. Yeah.
What's the like meaning by spontaneous?
I have no idea. I know it's something from gauge theory. I know it is something there, so I don't know if maybe some like time thing happens and like it breaks pretty fast. I don't really know.
I mean, I guess
I don't
the
get
only
it.
problem is if you had a time-dependent Hamiltonian. So I guess maybe it is related to
Yeah,
spontaneity in terms of time, but
I do know that the term like spontaneously like breaking does come from gauge theory. And from what I've seen a little bit is that you can also rephrase this in terms of like some gauge theoretical thing. And you do get the same kind of meaning of spontaneous. That is far off my field, so I'm not going to comment more.
broken is quite literally just that there are no.
Yeah. Yeah. And yeah. So some more stuff about, now I'm going to speak some physics or do my best at doing that, is that, okay, so I talked about the case of quantum mechanics, but actually a lot of the interesting, you can get some interesting results if you extend to QFTs, supersymmetric QFTs, where the axioms are going to be a bit different. So you're going to have some, now in QFTs, your momentum operator is, you know, you have your form momentum, which is now becomes an operator, and you know you can kind of measure mass in some way in QFTs. And what you can find is that if you have a boson-fermion pair, they have to have the same mass. So that's pretty neat. And in a QFT, the ground state might not be zero energy, it might be some positive energy. You're always going to have a minimum, but it might be positive. And in that case, you know, you might have, you know, if it has a positive energy, it's going to be. Sorry, let me not say something wrong. Okay, so what I'm going to say is that if the ground state has positive energy, then the fermions and bosons are not of equal mass. So usually when you look at the particles we know so far, none of them, if you look at bosons and fermions, they don't have the same mass. So that's why, you know, whether supersymmetry holds or not, it's not settled, but that is for physicists to look at. I like the math, and that's what I'm going to be focusing on. But yeah, so those are a few things you can look at. It's not so bad. You can actually do a good amount of math without knowing much QFT for these kind of things. But I'm not going to try to go there. In either case, even if you do the QFT case, you can restrict to where the momentum operator reduces to zero. So you can restrict to the kernel of the momentum operator, and you're going back to this case here, quantum mechanics. So whatever that means, if you don't know anything about that, it's fine. We're just going to stay in this setting that we've been talking about. Okay. So, okay. Now, if we have our theory, we kind of want to know if it's real or not, if it actually holds in nature. And one way to prove this is, you know, whether supersymmetry is spontaneously broken or not, is to know whether there are solutions to this equation. So according to Witten, at least in the paper, he mentions that this is the most important equation in supersymmetry, because this is kind of like what is the main goal of supersymmetry is knowing, does this exist?
What exactly is omega other than just some arbitrary state?
It's some ground state.
Just the ground state.
Is it? Yeah, he uses it omega for ground states for some reason. Yeah, no, just some ground state. But yeah, so it's the most important equation, and there's kind of a heuristic way to figure out whether we have or not bosons and fermions of the same mass. So, like I mentioned, if okay, sorry, give me 1 second. Okay, if there exist solutions to these, then there are, yes, if there exist solutions to this, then supersymmetry is not spontaneously broken, so there exist bosons and fermions of equal mass. And if, okay, I'm not a physicist, this is very, very annoying, I'm just gonna do the math. But okay, so let's do something cool about this. So if we want to know whether there are bosons and fermions of the same mass, what we can do is calculate the trace. So what is the trace? Okay, I'm going to do heuristics here. I'm not going to worry about the fact that this is an infinite dimensional thing. But in some way, I know that in positive energy, the bosons and fermions come in pairs. So I know that at least in positive energy, okay, so it's plus for bosons, minus for fermions. I'm really counting the number of bosons minus the number of fermions. And I know that in positive energy, they come in pairs. So this whole count is going to get canceled in positive energy. And all I'm doing is counting bosons and fermions in the ground state. Number of bosons with energy equal to 0 minus the number of fermions with energy equal to 0. So I've reduced my big count to just looking at the ground state. And if this is positive, then I know that they don't come in pairs. I know there are bosons and fermions of different mass, and I can know whether supersymmetry is spontaneously broken or not. So now this becomes an interesting thing to look at.
Hold on. What was the last sentence? So if you get 0, it spontaneously breaks?
Okay. So if supersymmetry is not spontaneously broken, then bosons and fermions have the same mass. For every boson of one mass, there's a fermion of that same mass. That's when it is not broken. To me, it's very annoying which one it is and which one it isn't. Because it's like there doesn't exist, it is spontaneously broken. I don't know, I'm not a physicist. But okay, so if it is not spontaneously broken, then there are bosons and fermions of the same mass, so this count is going to be 0. But if they don't come in pairs, there are things of different masses, then this is going to be a positive number. So, or a non-zero number, sorry. And now I know if supersymmetry is spontaneously broken or not by knowing this. So this is an indirect method. Of course, if I get a count 0, it doesn't mean anything. If I get 0 here, it could come or could not. Exactly. So yeah, you can have like a lot of weird thing happening. So yeah, and in the QFT case, like I mentioned, you could have the ground state to be a positive energy. So this count doesn't work in the QFT case. You could have a more general thing. If this is 0, you could have the thing you mentioned about no bosons and no fermions, because they're going to be in positive energy. Yeah.
Can you talk more about the object -1 to the power of f?
About the object -1 to the power of f?
Yeah, what object is it mathematically?
It's an operator. So this is a very heuristic thing. Don't take it literally. But it is the operator that I defined at the beginning. So it's and write it here. Yeah, and which is equal to plus. So it's equal to 1. Let's write it equal to 1 in H plus and minus 1 in H minus. So I'm just keeping track of if my state is a boson or if it's a fermion. I can just know it by this.
By what do you mean identity?
Yes.
That
I mean the identity, yeah.
Perfect.
Yeah. And yeah.
Sorry.
Oh.
I was gonna say, I guess you perform some like linear extension.
Yeah. And usually for this count, if you want to be rigorous, you have to add some factor of like some exponentially to the minus beta t or something like that. I know it's something from thermodynamics to keep like to make a proper count, because this thing here is like an infinite dimensional matrix of 1 and zeros. It makes no sense what I'm saying mathematically, but heuristically, this is what we want to do. And yeah, so this thing, this trace, either with this factor or not, is what people call the Witten index. And this is going to tell you whether supersymmetry is spontaneously broken or not.
Sorry, before we move on, can I ask, is this saying like, is the point that there's the bosons and fermions come in pairs when they don't have 0 eigenvalues? Or are there stragglers that are like canceling out somehow?
When there are no 0 eigenvalues, they come in pairs necessarily. They have to.
But this holds regardless of whether or not.
Oh yeah, this count here, this counting that I'm doing, yes.
Okay.
Yeah. So this is just a heuristic count I'm doing.
Can you explain how you did that again?
Okay. Yeah. Sure. Well, okay. So if I take the trace, this is a huge. You can think of it as a huge diagonal matrix of pluses and minuses. all the pluses are going to count for each boson that I have. So if I have a boson, it's going to be some huge diagonal matrix, right? And I apply -1 to this. I'm picking out that entry of the matrix. I'm going to have a 1 times this. So I'm going to be counting 1 boson, and so on. Same for the fermion. I have a -1. And if I take the trace, I'm going to be summing all of these over. I'm going to be summing boson plus boson plus boson minus fermion, 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 and infinitely many times. But like I mentioned, for positive energy, they cancel in pairs. For every boson, I have a fermion, so 1 plus 1 minus 1, 0.
Is there any like comments on convergence, or can we skip that and just?
I really want to like speak about the heuristic more than anything. For convergence, usually if you want to actually do math with this, you need the kind of regulation. Some factor here. I don't know much about that. But yeah, if you want to be properly do this count, but it's going to be a bit more annoying because now you're going to have like these. Yeah. But that's going to guarantee that you can do some you can actually do math with there, like sensible math.
But I mean, so in the work that they do, is it always done like this, or do they always just write trace of -1?
No, I think they do keep the
regulatory term.
yeah,
Okay.
they do it. Actually, from whenever I was looking around trying to learn about this, Witten on his paper was the only one who did not put.
You probably think it's trivial.
Of course, what is it gonna be? It's gonna be like, it's just annoying, like more details. Who cares? Yeah, but yeah, no. So everywhere that I saw, they did use the extra term there. All right. So that's my little intro to supersymmetry. So now we know why this is what we care about. We want to look, and again, remember, what are these with 0 Suki? So what have we achieved, or what is our goal now? Is to look at the 0 eigenvalues of energy, which is the same as looking at the 0 eigenvalues of my supercharges. So this is something we care about. Okay? Let's keep it there. Now, how do we do this? How would we look at the 0 eigenvalues of energy? This is a general thing. For a general Hamiltonian, this is hard. If you just give me some random Hamiltonian, it's going to be pretty hard to do this. People use something like with Dirac operators and all these things. You count some actual index for the Dirac operator, and then you go through the machine, but it's quite hard. But there is one case that actually can give you some interesting stuff, which is the one we're going to talk about. But before we go to that specific Hamiltonian, I have to give you a little crash course on Morse theory, because I will need it. Okay, so I will keep it to the classical setting. And what does Morse theory try to do? Morse theory tries to tell you, if you give me a function on my space, what constraints does it put on the topology? We know the other way around. If you give me a topological space, I know I can put some constraints on the functions. If I have a compact space, I know my function needs to have at least 2 critical points, because it has to need a max and a minimum. And so topology kind of puts some constraints, but the other way around, does a function put constraints on your space and so on? So it's this interplay between what constraints does a function put on a space. Okay? So that's kind of what it tries to do. And I'm not going to get...
Sorry if it's not too far, but when you say max and min, are you assuming more than a topological space in terms of structure? Are you assuming a norm vector space as well?
No, just if I have a smooth manifold and it's compact, it necessarily needs to, and you give me a function, a random function, it needs to have a maximum and a minimum. By compactness...
Oh, the function, not the
manifold.
Yeah,
no. Well, you're gonna have 2 critical points. So that's something you say about the manifold. 2 points on the manifold are critical points. At least 2, yeah.
And it's easy to talk about maximum minimums on R.
Exactly.
That's why we have max min.
Exactly.
For the function.
Yes. Yeah. So if your space compact, the image is going to be an interval. Interval has a upper bound, a closed interval. So you're going to have a upper bound, lower bound. These are going to be max and min. Okay. So I'm going to fix the setting to be be a compact n-dimensional manifold. And I mentioned the prerequisites are going to be just multivariable calculus and quantum mechanics. So whenever I say a compact n-dimensional manifold, I'm really going to be working locally most of the time. So just think of an open subset of Rn. Don't worry too much. Just think about open subsets of Rn. They kind of move around and glue to something curvy if you want. But don't worry too much about the details. And so I'm going to have the one that's compact, and I'm going to let f be a smooth function on M. So be smooth of class C infinity. Okay. Again, if I'm in a compact manifold, I need to have critical points. There's no way out of it, so I can fix a critical point. Let P in M be a critical point. Then I can define the Hessian of f. So then I have this Hessian of f at the point P, which is really my matrix of second partial derivatives in a local coordinate system. In general, in a manifold, this matrix is not well defined. If you change coordinate system, I could have a completely different matrix, but at a critical point, this is well defined. The extra terms are going to be first order partials with some curvature terms, and first order partials at a critical point are 0. So this is well defined for critical points, and I don't need a metric, I don't need anything for this.
William says has to be closed, no boundary for the maximum to be critical points.
Close no boundary for the maximum to be critical points. Yeah, that is true.
There are
Yeah.
easy Morse functions on any cylinder with no critical points.
Yeah, I'm not going to worry too much.
I just thought I should say his comments.
Yeah. No, that's good. But yeah, I'm not going to worry too much about those details there. Okay, but yeah, for this Morse theory part, I guess, yeah, let's add the assumption just in case. So let's add compact, no boundary, just in case. But just keep it simple. So just a closed manifold. All right. So now I'm going to tell you what a Morse function is. And I have this matrix. It's symmetric because f is smooth. So it's a symmetric matrix. It defines a symmetric bilinear form on the tangent space. So definition, f is a Morse function if for every critical point P of f, the Hessian of f at P if I have a critical point, I have this matrix, I can compute its determinant. It's a square matrix, bilinear, and if the determinant is 0 or not, I know whether it's singular or not. And for a Morse function, I need all these to be non-singular. Okay, why do I want that? It's because these are actually pretty nice functions, and you actually have a bunch of them. In a closed manifold, you have an open dense subset of Morse functions inside your space of functions, and they satisfy this very nice property, which is the Morse lemma. So why do we want these functions? It's because locally they look like this. If f is Morse, then there exist coordinates x1 up to xn such that x1, well, xi at p is equal to 0 for every I. So p is the center of this coordinate system, and my function looks like its initial value at p, and then some sum of squares, xi squared, I from 1 up to k, and then the remaining ones are going to be pluses. So it really looks like a quadratic form. So this is really nice. I have a function that I can look locally around critical points such that P is Morse. This is for every critical point, sorry. P, a critical point. So coordinates around P. So yeah, just some regularity stuff. I have a Morse function, I have a critical point. Then I can find some coordinates around P where my function looks like this. Yeah. Oh. That's an index. The xi, yeah, it's an index. Yeah, sorry, I'm a differential geometer at heart.
Yeah, I like that. Can you do has Morse theory been done without coordinate independent? Maybe using Riemannian geometry.
That's a good question. Okay.
Like
I've never seen that.
of covariant derivative squared or something with like H theory, so non-trivial covariant derivative, non-trivial connection.
Okay, so I'm gonna need to know a little bit what you mean.
Like this coordinate.
It's a coordinate independent. Yeah.
Expression. It's a very physicist way of doing it.
Yeah.
It's the coordinate independent way, like a pure mathy.
For this expression specifically, yeah, no. For this expression specifically, I don't think you can, mainly because like this is this really is the heart of the classical Morse theory, of finite-dimensional Morse theory. I don't know if you get an expression like this. It's a lot more complicated to do Morse theory on infinite dimensions, but no, I would say this is at heart is a coordinate thing. It's really the fact that locally looks like this. Yeah.
What's the point of splitting up the summation from I to k and then k to n?
Yes, so I want to get into that. Here's the thing. So if you remember some linear algebra, there's this result called the Sylvester's law of inertia. I don't know why it's called like that, and I never knew if it had anything to do with inertia, but it tells you that any quadratic form can be decomposed. You can find a new basis where it looks like this. And this number is unique. The number of negative entries in the diagonal is going to be unique, and the number of positive ones as well. So, up to a change of basis, all your quadratic forms in a vector space look like this, up to a change of basis for different k's. And this in some way tries to mimic that behavior locally in a manifold, because you have some very nice properties when you do that in vector spaces, and we kind of want to mimic that in manifold theory as well. Yeah. So, like I mentioned, this thing here is unique, and we call that the Morse index. So, K is Morse index of the critical point P. Okay. All right. So now I'm gonna say some stuff about Morse theory in general. I'm not going to be detailed about this because I want to get into Witten's results, and we're going to be doing Morse theory there, so I might as well learn it as we go there. But when you have Morse functions, you can actually know a lot about your space. You can actually find a full CW decomposition of your space just by looking at level sets. So if I have, for example, let's do something like this. This is a sphere, and the height function. So think of it as a sphere. I have critical points here, 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 and here. And if I start looking at level sets, if I look at everything that's height A and below, I'm going to have the following. It's going to look like this. I guess I should pick a torus more than a sphere. A sphere is kind of boring. But as I go up and up and up and up, it's going to start looking like this. Take something bigger, it's going to look something like this. And this whole thing, I guess, as you start crossing critical points, if you notice here this looks like a disk, but now that I crossed a critical point here, so here I have my critical point below, my critical point here, now I started adding something to my space. So this is the same as, so this thing here is to a disk plus, I believe, kind of a little handle there, right? I can just retract this to the sides and just kind of like start retracting it here. It's gonna look like this, and it's gonna start being like a thing here, right? It's gonna look like this if I just start stripping it down, and I can keep going at more. So now this looks like a disk, a D2, with attached an interval 0, 1 along the boundary, along like these 2 points. So some map here, some going map. And if I cross a new critical point, I'm going to be attaching more stuff. So if I cross a new critical point, it's going to look like this. So I've attached a new disk in here. I've just kind of like capped this one. And once you do the other one, you attach another cell. So what I'm trying to say with this is, as you start looking at level sets of Morse functions, you can get a full CW decomposition. So decomposition as a gluing of disks of your space. And you get a full information about the homotopy. I want to say this, yeah, that's what I'm worried about. But yeah, I'm sure you get a full information about the homotopy type of your space, and from here you can get like cohomological information as well. So that's what I'm trying to get at. Because the Morse inequalities are going to be something about the cohomology of your space. Did William say something?
Not yet.
Okay.
Might be typing. For the second picture you drew, is it enough homotopy, or even homeomorphism, or homeomorphic to the cylinder?
No, it's going to be a disk again, right? It's like this is it's just going to be like, this one?
Yeah, is that not homeomorphic to?
That's a cylinder, yeah.
Cylinder.
Yeah.
Okay, so the thing that you wrote is homeomorphic to, what is that? The basket thing.
So it's going to be a disk, and I attached an interval on 2 sides.
Is that homeomorphic to the cylinder?
I don't think it's homeomorphic, but it's homotopic.
You made the handle.
No, it's not homotopic, because pi one of that is Z free product Z, right?
Yeah.
How is that?
The cylinder also has Z, right?
Yeah,
They're both homotopic to a circle, right? If I just start like fix this line here and just start retracting everything to this line, I just get a circle.
Oh, yes. I thought there was something, but okay, sure. Yes.
Yeah, we're good?
Was the basket shape only because of the critical point?
Yeah.
Just to emphasize that.
Yes, it's very much because we crossed a critical point. So that's how you start going. You choose a right Morse function on your space. You start looking at level sets so that you can cross a single critical point at a time. You don't want to cross more than once at a time. And that's going to be starting to add either disks or intervals or stuff like that.
So why can't you cross 2 at the same time? Because like surely, I'm just thinking you take that shape, you lower the second bump to be level with the other one,
Yeah.
you'll cross 2 critical points in one level set.
I think maybe William knows more about what happens there, but what I know is going to be like what I'll say is this: is you can always find one where that doesn't happen.
Sure.
Okay, you can always find one that doesn't happen. I think the problem is that they're just not as well behaved.
Okay.
If you can,
I figured,
if you know that you can always pick a nicer one, might as well pick it.
You just want to order the critical points.
Yeah.
yeah.
Yeah, and when you start doing what Witten does, you'd really need to do that. Now you cannot cross 2 at the same time. This has to do with the index. You want to like tilt it in such a way that you can only go down to 1 index below. What I'm trying to say with this is the following. I can draw you a picture to enlighten the idea.
Well, you wanted me to make sure you say handle decomposition.
You get to handle the composition when you look at the level sets of your space. Let's take the torus real quick, and I'm going to put it upwards, and I have a height function on this. Okay. Now, I have 4 critical points. They'll have colors. Can I grab these? Okay.
William also says you can cross 2 critical points at the same time, but it's less organized, I guess.
Okay.
Yeah. For at least the, but I will emphasize this for the stuff that Witten does. You cannot do 2 at the same time. So here's the thing. If I look at the flow downwards of my function, so I have a gradient, I can look at the flow, and it's going to be, remember the gradient is the direction of steepest ascent. I looked at the negative direction of steepest descent. So my flow lines are going to be going downwards. If I start from this critical point, I'm going to start going down here, and same from the back, and have these 2 flow lines. If I take this one here, I'm going to go here, and I'm going to go here, have these 2 flow lines, and up here are these as well. Okay. And I have one that goes from here down below, here down below. So these are the flow lines I can make on this torus. There's a bit of a problem. It's the fact that it's not, maybe you don't know why, well, you don't know why this is a problem, but I can tell you a little bit, is that there is no, so for example, this one here has index 1 because it goes negative here, but positive here. It has an index 1 negative. Here I have index 1 as well because I have negative and positive here. This has index 0 because they're all positive, and this has index 2. But I have no flow line from an index 2 to an index 1. I always want to go from, I want to be able to connect all my flow lines from index A to index k minus 1. I want to be able to always connect these two, whatever happens. The idea is because I want to construct this moduli space of like flow lines that descend from one index. And nice, like the good thing about math is that we can actually do this by just tilting our torus. If instead of taking it upwards, I take it a little bit tilted, and I'm going to have a critical point here. I'm going to have one below, somewhere here in the back. I'm going to have one up here and one below. And now I can flow here more nicely to something of index 1. Again, here, index 1. And it also has index. It actually is going to look a little bit more on the side, but it's fine. So I can connect my index 2 to all the index 1 that I have. I can connect all my index 1 to all the index 0. Goes from the back. And I can also connect my index 2 to my index 0, but that one we don't really care about too much. We really care about the fact that I can connect from one to the next one.
So you just want to create a surface where you do have the connections between k to k minus 1. And even if there is a connection from k to k minus 2, we kind of just ignore it as long as we always have a connection from k to k minus 1. That's the point of the tilt?
Yeah.
Okay.
And you're always, when you're doing Morse theory, you're always embedding your manifold in Rn for sufficiently large n, and your gradient is of your height function that you take, right?
You don't always do this. Again, practice, yes, because Rn is the only thing we really know how to deal with. But you don't really have to. You can do
because gradient descent wouldn't make sense otherwise, right?
It makes sense on a Riemannian manifold. This goes our difference in philosophies is that the gradient is a vector field. So in a Riemannian manifold, you have if you have a function, you have your df, one form. But if I have a metric, I can put my one form as a vector field. I can just pass it through the musical isomorphism. And if I have a vector field, I have a flow. So I can look at flow lines, and I can look at gradient descent. So in Morse theory, you do care about vector fields being, gradients being vector fields, because you need them. You need those flow lines.
Okay, so you can do it without embedding it in.
Yeah, you don't need, all you need is a metric. That's all you need.
Oh, that's great.
Yeah.
That's great.
Okay, but so that was what I wanted to tell you about Morse theory. Morse theory is a whole thing that you can talk about. I could spend a whole course on talking about this, but I will not. And to end this mathematical interlude is just real quick, like I mentioned, your Morse function gives you a handle decomposition. So you get a CW decomposition of your space. You can get homotopy information, and in particular, you can get cohomological information. So just real quick as a reminder, I'm going to be working with the round cohomology. But if you do a whole set of dictionary translations, you can eventually have information about the space of closed forms, so omega k forms that are 0, mod exact forms. So etas in k such that, omega such that omega is equal to the eta for some k minus 1 form eta. And what do the Morse inequality tells me? So okay, so again, my Morse function gives me all this information. Give me a Morse function, I can find you this eventually if you give me enough time. And so now there's a question about what is the interplay between critical points and the topology of your space. And this is where we come to the Morse inequalities. Which is a very important topic in topology and symplectic geometry. And you have two. You have one, which are the weak Morse inequalities. These are the weak, which I will prove to you today, which tells you that the Betti number, so bk, which is the dimension of my k-theorem cohomology group, is going to be less than or equal to, this is less than or equal to the number of critical points of index k of a Morse function f on my space.
Are your cohomology groups of the smooth manifold always a Lie group?
Oh, it's a Lie group? Well, there are like a billion groups. I guess you can treat them as discrete groups. Sorry, they're going to be R's. Sorry, I'm talking about R's. Yeah, I guess. I'm not sure how that's used.
Okay. So you can always take dimension.
Yeah, oh, this is dimension as a vector space. Sorry.
Yeah,
yeah, this is a vector space.
Yeah, obviously.
Yeah.
I was wondering about why did we shift it?
Yeah, yes, you could think of it as a Lie group. It's going to be the same dimension, but maybe too overcomplicated. But yeah, no. As a vector space over R, and the weak Morse inequalities tell you that the dimension of hk is less than or equal to the number of critical points of index k. So that's the one I'm going to prove to you today. And there's the second one, which are the strong Morse inequalities, which these are more complicated. And this is really like the meat of Witten's work, but it is a lot more technical. It's that if you do the sum of minus 1 to the k, sorry, let's do I from 0 up to k. Yes. There you go. bk minus I is going to be less than or equal to the sum minus 1 to the I from 0 up to k, number of critical points of index k minus I of f. This is for every k from 0 up to the dimension of my manifold. These are the strong Morse inequalities. And these put constraints, topological constraints on your space. If you give me, this is huge. Give me a Morse function, I just need to count how many critical points. And I can start telling you constraints on my space. Counting how many critical points, it's easy. Give me your function, look at the derivative, count how many points I find in the solution space, I'm done. And it's gonna give me full, well, not full, but like a bunch of information about my space. So that's insane.
That is kind of crazy. Every time I see it, I'm always amazed.
Yeah, and this is a hard thing to prove if you're a mathematician. If you're a physicist, it's an obvious result. And I'll tell you why.
It's trivial.
For Witten, it's absolutely trivial. And so now I'm going to get into that. And funnily enough, something I find fascinating about his paper is how it's a simple idea. It's such a simple idea that he decided to do, and it just gave such a result. So let me properly move my page. So now let's actually get into Witten's work. Okay, have a good time. So the main thing, so the main I guess supersymmetry part really comes into the more strong Morse inequalities. For the weak Morse inequalities, which are both of them are trivial from using supersymmetry, but for the weak Morse inequalities, all we need is really just some perturbation theory. We don't really need much beyond that from quantum mechanics. So so let me first, real quick, this is going to be really fast, some Riemannian geometry just to set the stage. Okay, so let MG be a compact, so let's make it closed, oriented, so I need an orientation to be able to integrate Riemannian manifold. And if this is for people who only have multivariable calculus and quantum mechanics, what I really mean is that I have an inner product locally everywhere. And why do I want an inner product? Is because I want to integrate, and I want the orthogonality, and I want to look at all these things. And in particular, so once we have this, we can define, so if we have this, we have a volume form. Because of orientation, we have a volume form, and we can normalize it so that it respects our metric. So we're going to denote it by dvol sub g, which if you do physics, this is maybe a more common description that you've seen, that gij dx1 dxn in local coordinates. Could be. This is what I have in my notes, so I'm going to stress that, but no, it should be fine.
I think it should be fine because it's showing behavior Jacobian.
Yeah, I think this is fine.
I always forget
if it's this or 1 over this.
Yeah.
I think it's, yeah. Okay, so
Oh, that's right, because in GR we always working with the inverse metric, so you need the 1 over that. So
I
in
see.
GR you have 1 over negative determinant of that.
I see.
That's why.
Okay, thankfully I do not. But okay, if we have an inner product on a vector space, we have an induced inner product on the dual just by taking duals, and we can extend this to exterior products. So what I can do, once I extend it to exterior products, I can define an inner product on the K forms, and that's my main goal. So if I have two K forms, if I have omega and eta K forms on my manifold, I can define the following. What I can do, I can define the following inner product, which is going to be the integral over the whole manifold of, I can take the inner product pointwise at the level of vector spaces, and I can integrate it over my whole space. So I have an inner product on each tangent space, I have an inner product on each dual space, and I have an inner product from this on the exterior algebra. Yeah.
Sorry, I'm just a bit confused with the volume form, the dot dot dot.
Wedging all the coordinates.
Oh, wedge product. Okay.
Yes. Yeah. Yeah. If for most of the talk, don't think about it. This is just like I can integrate. So if you know about what this is, you can think about it. But if not, these are just worry about what I'm integrating here. This is just to like put it there. Okay. So, and just for completeness, this thing here is you can write it as in local coordinates. If I have G star of V1 wedge VK, and then inner product with W1 wedge WK, I have two K forms on the tangent space. So this is in a vector space. This is going to be the determinant of this huge matrix. So let's write it as G Vi Wj, where the lower index are the duals of the Vi. So Vi is a one form, or like a covector. I can take the dual, it's going to be a vector, and I could just take the determinant of this huge matrix I can make. That's that is inner product here. I can do that pointwise and then just integrate the whole manifold. And this defines an inner product on the forms. So again, this detail, I'm just adding it for people who might be a bit more interesting about certain details. I know you guys are, so. But if you don't know about these details, don't worry too much. Just know that it behaves like an inner product. We have norms, we have all these things, and that's what we care about. I'm just doing this construction so that people can know a little bit more. Okay, now remember that on forms we have our differential map. I'm going to omit the manifold because I'm just fixing it. So I can define a formal adjoint. So we define an adjoint of D by the property that D omega A is equal to this. So the formal adjoint D star by the property that this has to be the same as this. So I'm just forcing it to be this. And if you know some Riemann geometry, you have the hot star. You can do explicit construction with that. But this is hot star. The problem with hot star is that it's not easy to construct. So I thought let me just throw it. Yeah, you can just do it right away like this. And just as a quick example, this is in my notes if you want to follow the computations. There's more details in my notes if you feel unsure about something. But if I have a one form omega I, I'm using SI notation because I'm a physicist today. One form in Rn, then d star omega is going to be equal to minus delta j omega I, which you might recognize as the sum over delta I omega I, which is equal to the negative of the divergence omega 1 omega n. And similarly, I can start building more things. I can start building the Laplacian, which I'm going to do now. So yeah, first off, the d star on one forms is kind of is a negative of the divergence in Rn. And since I have a divergence, I can construct a Laplacian. So I have the Laplace-Beltrami operator. D star D. And this is self-adjoint with respect to my, because I'm just going to start putting stars on the other side and stars on the other side. So it's just going to be like, I define these stars to be the adjoints. So I'm making this forcefully to be self-adjoint. So we have that. And if you follow the same example here, so if f is a smooth function from from Rn into R, then you can compute this. I did it in my notes with excruciating pain. F, which is minus the Laplacian of f in the usual multivariable calculus. Okay, yeah.
It's really cool that this d plus d star squared is the Laplace-Beltrami, which is the Dirac operator.
D plus d star squared?
Yep. The square of d plus d star gives you the Laplace-Beltrami. So it's like the square root of the Laplace-Beltrami. In Lorentz signature, And in pseudo-harmonic manifolds is the Dirac operator. Up
Yeah.
to minus sign, so minus 1 to the PQ or whatever.
Yeah. So that's actually something cool that you notice. You can do that one, or the other one you can do is the following: is define Q1 to be D plus D star, just like you said, but I can do Q2 to be I D minus D star. And then if I do Q1 squared, I'm gonna have this, which I can call H if I'm bold. And I can do the same thing with my Q2 squared. And I can show that also these two anti-commute. So does this look kind of an idea of where we're trying to get at? We have a supersymmetric quantum theory. We have two supercharges. We have a Hamiltonian being our Laplace-Beltrami operator, and we can start doing supersymmetry now. So yeah, you have two approaches, that one or this one. And that simple change of mindset of like, let's think of K-forms as states, as either bosons or fermions, and let's think of this Laplace-Beltrami operator as a Hamiltonian. I have now supercharges, and I can actually do physics. And just that simple idea is like such a simple thing, but it really changed the perspective of a whole field.
And it's suggestive of the name, the Fermi-Dirac statistics, because that is the D plus D star is the Dirac operator, which gives rise to the Clifford algebra anti-commutative relationship. Hence the Fermi-Dirac statistics.
Yeah, it's some pretty cool stuff. And before I can continue on this line of work, I need to tell you about two results, which are the Hodge theorems, just because I'm going to be needing them for my counts. So Hodge theorem, just real quick, it's telling you that if I look at my H here, so let me call it HK. This is just a superscript, just to keep track that I'm acting on K forms. So the kernel of HK, which are the things that have zero Laplacian, so delta omega equal to 0. So we call these elements of this harmonic forms, and this is finite dimensional. So this one is finite dimensional. And two, any form, any K form, I can decompose it as something in HK plus something, the differentials of a K plus 1 form. Sorry, something's wrong. K plus 1 should be, this is a K, it should be K minus 1. I want to move it up. And then, yeah, D star. My notes have it the other way. For some reason, I made a typo. K plus 1. Okay. So any K form, I can decompose it as these. And my last little thing is, this is not part of the Hodge theorem, this is a corollary. It's that if I have a harmonic form, it has to be closed. I'll tell you in a bit why. And so a closed form is going to be, I can inject into the kth de Rham cohomology group. You can show that they preserve the boundaries. And so this is an isomorphism.
The HQ there is the closeness with respect to delta, right? But the de Rham is with respect to the exterior derivative.
Yeah, exactly.
Closeness with respect to the operator.
Yeah.
And the C derivative close.
Exactly. So just to convince you real quick that if you have a harmonic form, it is exact, just real quick, we can use our inner product. So if I have omega, sorry, what am I trying to do? Okay, so this thing here, this is equal to 0 if and only if omega eta equal to 0 for every eta. But this thing here is going to be d star d omega eta plus d star omega eta. And I can start moving the adjoints on the other side. So d omega d eta plus d star omega d star eta. And if I replace my etas by omegas again, now it's not an if and only if, it's just an if. Then now I'm going to have the norm of d omega squared plus the norm of d star omega squared. And this is equal to 0 if and only if each one of these is equal to 0. So harmonic form has to be closed and co-closed. Okay, that's all I want to tell you real quick before we get into our supersymmetry. Okay, now let's actually do some cool stuff. So yeah, like I was saying, the big thing that Witten did was, it was fascinating. Just do this quick change of perspective. Think of K-forms as being states, either bosons or fermions, and I can know which they are because of this decomposition. Sorry, no, don't say that. No. Just whether they're even or odd degree. So if their degree is even, I'm going to think of them as bosons. If they're odd degree, I'm going to think of them as fermions because each form has a degree. Okay, and we can do physics now. So let's recall our goal, what it is. Our goal is to prove the Morse inequalities, which I'm going to write here just to keep them track. So I'm going to show that the dimension of hk deram is less than or equal to the number of critical points of a Morse function of degree k. So Morse function h. But now by the Hodge theorem, I know that I don't need to look at the full Deram cohomology group. I can focus on the harmonic forms. So this is going to be the same as the dimension of harmonic forms. So I've reduced my problem to looking at the kernel of H, which is my Hamiltonian. So I'm looking at zero energy eigenvalues. Okay, so our goal is now to look at zero energy eigenvalues over Hamiltonian. And the hard part about this is, how do we get information about a Morse function? Where even is the Morse function? I just gave you this algebra, right? Where is the function? So the way we do this is by degenerating our algebra. So we're going to define a new one just by changing it a little bit. So we're going to conjugate by these operators, so by these functions. Sorry, no, I'm going to define d sub t to be this, d star sub t to be adjoint. And I can redo the whole thing. So I can have my q1t to be equal to d plus d star, q2t, dt minus dt star, and my ht, which is going to be my qit squared, which is dt star plus dt star dt. I just deform my differential. The idea is because now, if I choose h to be a Morse function, I'm going to be keeping track of the degrees by t in some way. So I can use t to keep track of the critical points of h, and I'll explain why in a bit. Well, I guess you can explain it intuitively right now. If I do so again, I'm thinking of this as applying in a form, right? So here's going to be this times this when I apply it. And if I take the derivative here, I'm going to have the chain rule. So it's going to be h, it's going to be th e to the ht, and sorry, t dh. So now I have a dh where I can look at the critical points, and I have a t to keep track of the order of things happening. So the goal is to start doing perturbation theory with this thing. Okay. So just as a quick sanity check, just to Quick example. I wish I would have gone to the examples with a bit more detail, because again, to me, when I was doing this, I was just like writing stuff down. I was just, because Witten is quite brief. I'm like, I'm gonna play with it, and you find some cool stuff. So if I take the example of f being in a smooth function on Rn, and you compute these things, so you find that ht of f, I wish I would have done it on the spot, because like when you see it, it's like, what? But if you do the whole computation, you're gonna find that this thing here is equal to t squared, the norm of the gradient of h squared, minus t, the Laplacian of h, and here should be an f, and then minus del squared f, which I'm going to reorder as minus nabla squared plus t squared. Here I'm missing an f too, sorry. This applied to f, and then plus this kind of random thing applied to f. Does this thing look familiar as a Hamiltonian? Everything in the universe, what is it? It's a harmonic oscillator. This is a harmonic oscillator. Sorry?
Kinetic minus potential, or other way around.
Yeah, so here you'd have your kinetic energy, and here you have your squared thingy. I guess you need to expand it in coordinates. You're gonna have like dh, dxi. You have some square stuff going around, but it's a harmonic oscillator.
I was way off. It's okay. Harmonic oscillator is a solution to the Schrodinger equation. So,
Exactly.
Yeah.
So, but you can start seeing why we want to do perturbation theory, because we have this, something that we know, and we have this extra perturbation term here. So this kind of like weird thing that's happening here. So you're gonna have to do perturbation theory to try to restrict to higher order terms, or yeah, leading term expansions. Okay, so in my last 10 minutes, although we did start a bit late, so maybe I'll. Thank you. I just have like, this is my last page. This is my last page. Okay. Thought I had more to say. 27 minutes left. Oh my god. I have plenty of time then. I should have gone through the exercise in detail though. Oh, now I'm cheesed. But yeah, so now we kind of, okay, so I guess I'll be able to say a bit more about this. So let's think about this real quick. If you notice, when you make t go larger and larger and larger, this thing here starts taking over. If I make t go huge, this thing doesn't really matter, so it's order 1. This thing is a constant, and so this thing takes over. But now this thing here is the gradient of h. So this has the information about critical points. Critical points are points where the gradient vanishes, right? Are we okay with that? Yes. So as I boost my t to some huge numbers, I'll start concentrating at critical points. This is where the information is at. So this hints as to what we want to do. We want to, ideally, if the more general expression looks something similar, we're going to start taking t to be huge, and we're going to start having restrictions on this thing, on critical points, and what behavior can they have. And I'll be more precise about that right now, what I try to say here. But before I do that, we need to find a general expression for this. But okay, first, just as a few facts that I'm not going to be able to prove, but they're quite easily provable. It's just a bit of an annoying computation. I can start looking at the same cohomology groups, like these twisted cohomology groups, to be the kernel of dt, mod the image, mod so omega equal to dt eta. I can start doing the same thing I played before, just without these twisted groups. Sorry, and I have my DT map, and I can look at the Betty number for this, which is going to be the dimension of HK, my deformed cohomology group. Okay, so at different T, I might have different dimensions a priori, but the truth is that this is not the case. I can define this map. So what I'm going to say is the map psi that takes a form, maps it into e to the minus h, induces an isomorphism, an iso of my usual de Rham cohomology groups, my twisted de Rham cohomology groups. So even though I'm deforming my structure, the dimension stays constant. So the fact that I want to bring my T all the way up is not going to change my Betty numbers, but I'm going to have more control over the critical points. So I can play a bit more freely with this while still keeping my Betty numbers intact. So that's pretty cool. And you can repeat Hodge theory with my new complex. So here I know this is the Hodge. This is going to be the kernel of HK. Of my Hamiltonian, sorry, I have it, let's call it H. It's going to be the kernel of H. I can do Hodge theory again here with my deformed one when I have the kernel of HK, of HT, sorry, my deformed, the Hamiltonian. So now, I'm back again at doing supersymmetry with a deformed Hamiltonian. So my goal, the thing that I had here about looking at this kind of harmonic oscillator plus some random thing going around is a valid thing as long as I have a general expression similar to this for my deformed Hamiltonian. But the idea is going to stay intact. I just need to look at zero energy eigenstates of my deformed Hamiltonian, and these are going to be the same as the zero energy eigenstate of my usual Hamiltonian. So my Betty numbers remain all the way up and control my critical points. Okay. Yeah, this guy's a genius, I'm not gonna lie.
I think it's all on the level of just vector spaces, right? Well, k-fix 0 power of vector spaces.
Sorry, what?
Especially the injection that you had from HK to H theorem.
Yeah, it's as vector spaces. At the various vector spaces, I think you can make it as the level of like probably infinity modules or something. I think it's going to be the same thing. But yeah, as vector space is fine. Sorry, at the level of infinity modules, because you multiply by functions, so it should be fine. Yeah. Okay, so that's pretty neat. Okay, and now, okay, I'm afraid I'll have to skip computations. Well, actually, this one I'm going to skip because it is a very annoying one. I did it fully, and it was not fun, so I will not endure you through the pain. 21 minutes, more than enough. But what I will say is the following: is I can. Oh man, this guy's a genius. So let E1 up to En, my manifold is oriented, so I can define an oriented basis, or oriented. Sorry, positively oriented frame, local frame. This induces a positively oriented local frame in the dual space. And I'm going to define these operators. I'm going to let me make sure I'm not mixing them up. A K to be an operator from the K forms into the K minus 1 forms, which take a form, a K form, and I'm going to do the interior product with ek standard basis standard element of my frame. So I have this one, and I'm going to define its adjoint. So a k adjoint is going to be from k minus 1 to k, which instead is going to be the wedge product of it. So this is going to be mapped into the wedge product with the kth element of my frame. So this is something that the kind of stuff that you have to just be too smart to know why, because they're raising and lowering operators. So yeah, so usually you call this one a fermion. Which one is it? This one's a fermion creation operator. This is a fermion annihilator operator. Yeah, you just have to know that. I could have never guessed that. But once you have these operators, we have a general expression for our twisted Hamiltonian. So I can write this as d star plus d star d plus t squared is going to be dh squared. I'm going to tell you what this is in a bit, but you can kind of guess a little bit from the previous example. And here I'm going to have an order 1 term where I'm going to have some covariant derivatives. And a commutator. Okay, so let's parse this real quick. Just let me mention that this here is our original h. Plus t delta I, nabla I, nabla j, h, and commutator. Okay. So here we have our original Hamiltonian. We have some extra perturbation going around. This thing here is, just to make it explicit, is really the Gij of delta del jh. So this is the norm, more generally for the Levi-Civita connection. This is the nabla is the Levi-Civita connection. So it's the norm of the derivative of h. So again, what do we have? Or I guess this here you can write it as your nabla, your kinetic energy. Yeah, just keep it there. You're gonna have your kinetic energy. You're gonna have this this t squared that kind of looks like a harmonic oscillator, and this kind of number operator. You have a creation with commutator with an annihilation operator. So this is kind of like counting the numbers of things going around. Okay. Now I'm gonna make precise what I meant by, as I make t go up, I'm gonna start concentrating on the critical points. So what did I mean by that? To me, actually, that was very annoying because Witten writes that very casually, and it didn't make any sense to me until I had to play around with it. But note the following. Sometimes I wonder if does he do it like in his head?
He does it always stuff.
Truly insane. So if we have a zero, remember we're trying to look for zero eigenstates. This is what we care about. So if this omega t is a zero eigenstate, then I know that the following is true. No one can doubt me about that. I can expand my ht like this. So I'm going to have h omega t. Sorry, there should be a t. Omega t. I'm going to have a t squared of my dh squared and omega t squared. Again, here I really mean okay, but by square here I really mean like the square with the metric. So like the inner product of it with itself, plus t, and here inner product I, j, h, a, I star, a j, omega t, and omega t. Okay, this is a bit of an annoying expression. I just kind of expanded my ht. But as I make t go up, this thing here doesn't. The only thing that depends on t here is maybe this guy here, but it's going to be relatively constant. As t go up, this is also not going to change too much. This one here is going to take over. As I make t go larger, it's going to look something more like this. It's going to behave like the following. This takes over. But it's supposed to be 0. So what's the problem? The problem is as you make t go up, for this to be 0, you kind of need the support of your omega t's to start shrinking. So here's my critical point. Take a critical point. So the only way for this to be 0 is if I'm close to a critical point. Otherwise, this is always going to be positive. Because this is going to be non-zero, it's going to be non-zero, it's going to be going positive. So we need to be close to a critical point, so that P be a critical point. And as we start making T go higher and higher, the only way for this to go 0 is if as I make T go higher, this starts getting like smaller and smaller and smaller, the support. So my support has to start being shrinking and shrinking and shrinking and concentrating to my critical point. Start like a kind of like a bump function. Start getting like that. So that's what's happening, as the 0 eigenstate starts localizing all the way in the critical points if we make T go large enough. Okay, so now how do we start controlling the critical points is by looking at the eigenvalues of my Hamiltonian. Okay, because of this, I know that I need to worry about I start looking at the critical points. And again, I'm trying to solve this energy 0 eigenvalue. So let's start looking at our eigenvalues for Hamiltonian. So let lambda n kt, this is a lot of notation, is b, the nth smallest eigenvalue of ht. So again, my ht has eigenvalues. I can start ordering them. Take the n one here is going to be the n smallest. So lambda 1 is going to be the smallest. Lambda 2 is going to be the second smallest, and so on. And they could be repeated, by the way. It's not like distinct eigenvalues. And our goal is to count how many of these are 0, because that's what we care about. And also, just heuristically from this argument, as we start shrinking and shrinking and shrinking, we should expect to have only one eigenstate close to this critical point. For each critical point, we should expect to have only one eigenstate at the 0, at the ground state for each critical point. So, okay. If we count the number of 0 of these, we get the Betti numbers, because the 0 of these are the kernels of HT, which is the same as the kernel of H, which is the dimension of the rank cohomology group, our Betti number. Are we following? Are we okay?
There's a question online.
Yeah.
Who asks, I'm confused about the oriented frame in general. You can't choose n linearly independent vector fields. So for an orientation, you need to specify local frames, but then as such, there is no globally defined kth basis element because you're making non-continuous choices. So I guess my question is, why are the alpha operators well defined?
I see. Okay, sorry, yes. Yeah, okay, no, so, okay, yeah, I should have specified this is locally. Sorry. These are not globally defined. You really want to restrict to lower. You can always find an oriented frame, that you can always do, and just restrict to that neighborhood of where your frame is defined. Yeah, sorry, thank you for catching that. Okay, so now let's do Morse theory on our H. So suppose H is Morse. So what does this mean? And okay, also just some regularity conditions, so like or niceness conditions. pick coordinates where our metric looks like Gij is going to look like a flat metric in order 0, and then everything else is in order 2. So something that doesn't have no order 1, you can always do this. And then we can also locally write h5 to be h0 using our Morse lemma, but since we took this extra condition, we might have some extra order stuff to worry about. So we're going to have these lambda i's, phi I squared, and then plus stuff of order 3. So these lambda i's are either plus or minus, depending on the sorry, no, these lambda i's are just lambda i's. This is not a Morse theory thing, sorry. This is just take these things, and you can also make them so that the first derivative vanishes. The order 1 vanishes. Sorry, yeah. Okay, you actually do need the Morse lemma, but it's a bit more annoying to deal with. So don't worry about it. You might not have plus or minus 1. You might have some other stuff here. 9 minutes? We're good. So okay, once we have this, let's put it back into our Hamiltonian, into our HT, and just kind of like do perturbation theory. So if you replace in your HT here, I can replace my H by the expression that I have, express my H by the expression that I have, and just go through the motions. I'm going to have that H sub t is going to be equal to something of order t, H sub t bar. So it's going to have something of order t. Then I'm going to have something of constant order. I'm going to have something of order 1 over t, p1, and 1 over t squared. So I'm doing an expansion over 1 over t, p2, and so on. So these are perturbation terms, and this is my leading order term. So what we're going to do is analyze this leading order. And you can show just by this same thing, once, like, literally just plug it on the machine. And you find that this HT bar is the following. It's going to look even more like the thing that I've been hinting that things are looking like. Where now I'm in local coordinates, so it's going to be del squared, if I squared, plus t squared lambda I squared by I squared. This is 1, and my ki, or kj, let's write it, aj. Does it look more like a harmonic oscillator now? Yeah. Yeah, so again, everything is a harmonic oscillator. And we know the eigenvalues of this because we've done it a million times in physics. So the eigenvalues of hi are t lambda I 1 plus 2 ni. So I need to add all the constants that I'm dealing with in my potential, where ni goes from 0 to and so on. And now this one here is okay. Also, each one of these appears with multiplicity 1. We remember this from this has a discrete spectrum or something like that, point spectrum. They appear with multiplicity 1 as well. Now this one here is kind of this this number operator, and you can show that also just by computing it, literally doing wedges and contractions, that this thing here, ai star, ai omega is equal to omega if ai, sorry, if ei is in the expansion, of omega, and it's equal to -1 otherwise. So this thing here really keeps track of whether I have an EI in my omega or not. So it really is counting, do I have an EI or not? Also, these two operators commute. This one here is acting on like the function part or the spatial part, while this one here is a wedge product, like I'm wedging and contracting, so this is going to act on the wedge part of things. Remember that a form looks like a function, and then some dx1, or here would be like EI wedge EJ. This H acts on this, and this KJ acts on this. These are disjoint, so they commute as actions, and mutually can mutually, well, not diagonalize, but mutually. How do you say it? Sorry. Yeah, diagonalize. Well, yeah, is the eigenvalues of my HT bar is going to be the sum of these two. That's what I'm trying to say. So I'm wrapping it up. It's almost done, because now we have our eigenvalues, and this is where the magic happens. So the eigenvalues of H bar T, these are T, the sum over I of lambda I, absolute value, 1 plus 2 ni plus lambda I n sub I. Again, goes like this, and n sub I is equal to plus or minus 1, depending on what I mentioned before. So also, this is where it acts, this is as an action, as an operator on all the forms. If I want to stick only to K forms, because that's what I'm looking at the space of K forms, I'm going to need, well, omega is a K form, K EIs in its expansion. So the number of positive that I have need to be K exactly. Number of positive, let me make sure. Yes, so the number of positive n sub i's in there have to be K for the action restricted to the K forms. Are we good? Because again, this counts the EIs, and for this to be a K form, it needs to have K EIs. So I need K of the n sub i's to be positive. Okay, but again, I'm looking at the 0 eigenvalues. That's what I care about. So how do we get 0 here? Well, this one here is going up. So I for sure need n sub I to be equal to 0. So this is 0 if and only if n sub I equal to 0. That's one condition. So that gets rid of this, because it's going to be pretty big. It's going to be bigger than that. This is only plus or minus 1, so I need this to be 0. And now I need these two to cancel each other out. So for that, I need that ni to be -1 whenever this is positive. If lambda I is positive, I need this to be a negative lambda I, so I can cancel with this and get a 0. Yeah. Yes, it should be. Yes. Sorry. Yeah. Yes. So yeah, this should be 0, and I need n sub I to be negative whenever lambda I is positive. So what does this mean? First, this already means that there's the 0 eigenvalue only happens in multiplicity 1. There's only one configuration where this happens, is when ni is equal to 0, and whenever this is -1, whenever lambda I is positive. So that tells you that multiplicity of 0 is 1. And the only way for this, again, remember that the lambda i's come from your Morse function. So the number of positive it has is going to be related to the Morse index. So if you do the counting, n sub I is -1 whenever this is positive. So n sub I has to be positive whenever this is negative. So okay, so that means that the K forms that are in the zero eigenstate are exactly those that have Morse index K. Because they have to have a negative, this has to be positive, so this has to be negative, this has to be positive. So if I have K positive ones, I have a K form, remember? If I have K positive ones, it's a K form, and this has to be the number of negative ones is going to be the Morse index. Good. So so if and only if this is equal to 0, and I is equal to 1, if and only if lambda I is negative, and so this implies that around each critical point of h bar sub t, there exists only one zero eigenstate, because multiplicity is just 1, so I have only one zero eigenstate, and this eigenstate is a K form if and only if the critical point, the index P is equal to K. Okay, we're almost done. So this was for a single critical point. We kind of isolated it out. But if I do it for every single one, what I get is that the number of critical points, so the number of eigenstates, of zero eigenstates of degree K for this h bar t has to be the same as the number of critical points. I have one for each critical point. It's a K form, has index K. So as I count the number of critical points of index K, I'm counting the zero eigenstates of h bar t, right? But h bar t is just a first order perturbation of h sub t. So the fact that this thing here is a zero eigenstate of this doesn't really mean that it's a zero eigenstate of h sub t. This is just a sort of perturbation. This has high terms that are going to make it non-zero, probably. So what does this mean? This means that we have our Morse inequality. I'll write it nicely as a wrap-up line, is that the number of zero eigenstate in degree K of h t bar, this has to be the same as the number of critical points of degree K, of index K, of my Morse function h. But this is a first order perturbation of my h sub t. So the number of zero eigenstate is less than or equal. So this one here kills all the eigenstates in each critical point, but my other h sub t has more stuff, so might not kill them all. It has to kill at most. It has to kill a subset of this. This is less than or equal to the zero eigenstates in degree K of h sub t. And this thing here, as we settled, is the Betty number, b sub k. So we get a Morse inequality, a weak Morse inequality. So it really is just a perturbation theory argument.
Is there a reason why Witten even did this? Or was he just kind of, he realized he could and did it? Or...
I have my suspicions. So I believe it requires a lot of creativity. I definitely believe that. I am under the suspicion that it's partially also a product of its time. I think when you do product of its time. So like I think when you're doing all these perturbation theory arguments, and usually that was a big thing, I think in instantons back in the day and stuff like that. I think it's common to like keep track, like put these exponentials to keep track of the order of things.
Yeah, I mean, I've definitely seen that before.
Yeah, it's a common tactic.
Trick.
Yeah. So I think he was just creative enough to try it on this one, and it worked out very nicely.
Also, the more familiar you are with both the math side and the physics side, the more you can draw connections between
Parallels.
Yeah.
That's true.
To me, that's like the biggest like interesting part is like, you know, just how he was like translating from one language to the other. He's like, yeah, sure, we all think about harmonic forms. If you're a differential geometry, you think about harmonic forms. You don't think them as zero eigenstates. You don't think of K forms for even degree as being fermions and bosons and stuff like that. So I think that's truly like something that is not wasn't done much, if at all. So that's quite fascinating in my opinion. And you know, he does do more stuff. This is like this thing here is just a couple of pages in his paper. This is barely anything. His paper is longer. He does a lot more. Like he does get pretty hardcore afterwards. This is like the baby part of the paper. But even then, like just the ideas, just these simple ideas are quite fascinating. Just change of perspective, and they give you these things. Yeah, so that's what I would say. Any questions?
Wow, I just saw the ball spike. We started clapping.
I have a question, but it might be best to ask it last. So if anyone wants to go.
Sure. Yeah, I was going to ask about when you were filling up the manifold of water.
Yeah.
So I guess there was that question of like, what about when they're at the same elevation? Well, okay, actually, first of all, you talked about like this idea of the Morse function, and then you're talking about elevation. I assume that we're taking the Morse function there to be like the elevation.
Yes.
Yeah. Okay. So is there always some like small perturbation connected to the angle to put them off?
Yeah, you can actually make some pretty cool stuff. So the condition to make them like tilt a little bit is something called the Morse-Mel property. It allows you to make these transversal, because what is really happening is okay, it's unfortunately a bit more complicated to explain. I just thought of the arguments a bit more complicated, but the idea is you can always perturb it so that you can do these things, and you have these transversal intersections. I guess I'll briefly explain. Is when you have your torus, and you look at the downward flow lines, you have two. If you have a critical point, say let's take something interesting like here, you have something called the unstable manifold, which are where flow lines tend to go away from, and you have the stable one, which are flow lines that want to get into this critical point. And usually want these for two different critical points. You want these to intersect transversally, which is something meaning that you want the tangent spaces to like the sum of them span the whole thing. And so if you look at the case of this one here and this one here, so I forget about this one, that was my problematic point. On the other one, it technically is transversal, but it's because it's empty, and we don't want that. So you can always, so there's a couple of things that could go wrong with transversality. You either get something dumb like this, where the intersection of the unstable manifold and the stable manifold. So the unstable manifold for this would be just this, while for the and the stable one would be, this would be the stable one, sorry, and the unstable one here would be here, here, or down here. So it misses completely the center part. So
why is it missing the? Sorry, why is it missing?
Because you can never find a flow line that goes from here to here directly. You cannot. Yeah, it will either try to go here or it will try to go here, but it will completely miss any flow line that wants to go here. But yeah, what it's and this is one of the bad things that could go wrong with transversality, is just like some dumb. It's transversal because it's empty, which is a dumb argument. But you can have more bad stuff going on, and these perturbations allow you to keep transversally, like behaved.
I'm thinking like in higher dimensions, you can definitely make some funky manifolds. But so then the question is, or maybe you already answered this, and you're talking, I must have missed it. Are you always able to tip, rotate, or do whatever in higher dimensions such that you will always be able to have a decreasing by one order index flow line?
Okay, I guess I'll have to ask about what do you mean by. Is your question if I embed my manifold, if I have a Morse function, if I fix a Morse function, and suppose that my manifold is embedded, can I only rotate it and just rotate it and these like affine transformation to get a new one, or what do you mean? Or if I can find a completely new.
I could rephrase it like completely like thing in terms of like, is that tilting always possible to do?
Yes,
Okay.
you actually have an open dense set of these. So any smooth function, I can approximate it, even if it's not Morse. I can approximate it to a Morse function that is very nicely behaved.
And then you can.
Yes.
Okay. Yeah.
Yeah, you don't need to embed. This is a pure.
Yeah, sorry. I wanted to be more.
You,
Because then you get more funky objects.
you still want to avoid things because you want to avoid a lot of things. If I have a sphere, this is a critical point of index 2, index point of index 0. I don't even have something of index 1.
Yeah.
I want to avoid that too.
Yeah.
So
Like some shapes don't even.
yeah. So yeah, you always want to do these kind of things, and you always can.
Convention with the index.
The minus one.
Yeah, because like, you know when you go to the minus and then the positive.
Yeah,
Is
usually
this convention or is there a reason why?
it's convention. It's because you want to think of the flow lines going downwards.
Always okay.
So the minus
That's why
is
minus
like
something
going
weird.
down. Yeah. So that's what you want to think about.
Okay.
Maybe this is a stupid question, but is it obvious why it's like invariant?
It's a stupid question. I'm kidding.
What do you mean by invariant?
Like,
Sorry.
okay, if I find, I guess like, like you're trying to find something that the flow is
But it's
one
not
after another.
Because like when we.
Yeah, that's what I mean. But I mean like, okay, invariant over like the nicest possible.
So like.
What is invariant with
what is
respect to
invariant?
what?
Mm,
Like the index? Because the index is not invariant.
well, no, the index is would be right.
Well, I thought the whole point
No.
was that you could tilt it.
Yeah, it's not invariant. Yeah, so here you have index 2, index 0, but you're waiting a new one with index 1. This one, index 1, index 2, index 0. Yeah, you always want to get ones that are like orderly. Highest.
Right. Yeah, but as long as you do that, then it like you can't have.
Oh, I can create more. I can do more of these, right?
You
Just,
don't make one that's even worse than that. Like you just make one that's nice, but you can't make it worse.
yeah.
Like you could start with that one and then go to the sphere and then you make it worse. Okay.
Yeah, there's no invariance. What you do have, so here's the thing: the index itself doesn't index matter for you to count something else that is invariant. So what you want to start counting is the space of trajectories. So that's what Witten does in the second part of his paper. Is there's the 3 parts in the paper, by the way, but the second part is, well, let's think about the space of all flow lines that go down, and this thing here you can. If you define that space, as long as they go like down by one index, you can define, this is a moduli space, you can define a dimension for this moduli space, and that dimension is counted through the index of the points. So you're going to have a difference of indexes, and this is going to be invariant. So of flow lines, gradient flow lines. So you start doing that. So for example, if I look at okay, here I have. See. So if I look at the space, I'm going to look at the space of flow lines. So let's look at the space M. Let's say this P, this Q. I'm going to look at the moduli space of flow lines from P to Q. And again, now P and Q to have index difference by 1. So this is going to be the space of all flow lines that go from here to here. I only have one, unfortunately.
That is one in that case, even though they're like the way you've drawn it. This one's at higher elevation. They still have a difference of one.
Yeah, because it has index 2, this has index 1, right? This has two directions where I can go downwards, like this and then. Here I only have one direction to go downwards. So it has index 2, index 1. And the dimension of this moduli space is going to be the index of P minus, okay, here you usually want to like mod out by translations because I don't want the, okay, if I don't mod out by translation, I'm going to have this whole line. So it has dimension 1. It's going to be 2, 1, it's going to have dimension 1, meaning it's this whole interval in some way. And if I mod out, I usually want to like think of the line itself, so I don't care about parameterization. So I should mod out by R.
Wait, what MPQ is the line? Or
Yeah, MPQs is the line.
okay.
And I want to,
It's the space of all flow lines, right?
Right. Okay. Yeah.
like counting like shift. Because if I mod out by the R action of like shifting in time, I'm keeping track of the whole thing, right?
Do we want to also mod out by other things, homomorphisms?
No,
Actions to make a stat.
No. For this one, you really only want the translations. Because if you have, okay, again, the line has constant. If I have, let this be the flow line, it has the speed is fixed because I need it to be the gradient. The speed it has the gradient of gamma. Sorry, the gradient of my Morse function. So that's fixed, and I want to gamma t. This is a line, but gamma t is my line. But gamma t plus c defines the same line. So I want to think of these two as being the same in my. So I mod out by this translation action. And so if I don't do that, I have one dimension, but I really care about the one that's 0 dimensional.
Okay.
So mod out by R, and then I get 0. So the dimension is that. And this is how you start doing something called Morse homology. So, yeah.
Two questions. First, the Williams question. When you do the even forms are bosons and odd forms are fermions, then the Witten index, is it just the Euler characteristic?
My understanding is yes. I don't quite recall. I don't think I can say for sure yes, but I am pretty sure it should be.
Okay.
I have to. Yeah, I'm pretty sure it is, but don't call me too much.
Right. And the Witten index is a index in the index theory sense,
Yes.
either analytical or topological.
Yeah, you can make it. You can make an actual operator, and it's going to be the index of that operator. Yeah.
Very nice. Very nice. The operator being the -1 to the f.
No.
It's different operator. On some different Hilbert space, right? Because like in the analytical index is co-dimension of the co-kernel or something of an operator acting on a Hilbert space.
I don't know much about it, but it's a fermion operator. I looked it up earlier.
Fermion operator. So it's an endomorphism on what?
The inverse temperature.
Okay, so.
But like what you're right, like the trace -1 bf e minus beta h says that it's inverse temperature beta is defined as modification of the standard position function. That's what the Witten index is.
Okay, but I want to see it be written as either the analytical being the kernel thing, the dimension of them, or being the Chern class or subtodd class or whatever, or analytical index.
Okay, maybe we can look at the answer here. But my vague recollection is that you can create a differential operator that keeps track of this. It will be the differential operator.
And this index there, index of P, the Morse index, is not an index in the index theory sense.
No. Actually?
Is it?
No. Is it?
It's not topological, right?
No, it's not. Yeah, no, you
Because
can
if
make
I
it.
tilt it,
Yeah.
it changes, and
Yeah.
the index in index there should not change.
Yes, but you can do something else though. You can. Here's something you can do is no, this Morse index is not an index operator in the other sense, but you can relate it to some. Okay, what I'll say is this: is when you look at the differences of indexes, you can pose that as also a differential operator problem, as a solution of some differential equation, and that's going to give you some moduli space, and the moduli space will, the dimension of it's going to be given by the dimension by the index of that differential operator. You can
what of that? Sorry.
Yeah. So the thing I wrote before about this moduli space of flow lines, it's a difference of things, and if I look at more general things, I can pose this as a differential equation problem.
Yes.
Which is the same as a differential operator, a solution to a differential operator problem.
Yes.
And the index of that will give me the dimension of my moduli spaces as an index is a differential analytic sense.
That's beautiful. And is it still the modular space of flow line?
Yes. Yeah, you get recover the same information. Yeah, but
so yeah, the difference of indices we can recognize it. That's crazy.
Something I will mention because like a lot of this stuff you could do it like without the moduli space, but what changed with Witten and Smale, because he also did some work on that, is that posing it as a differential operator problem allowed us to do it in infinite dimensions afterwards, because it was done before it was done like using the topology of the space, but now that we pose it as a moduli problem of a differential operator, we can actually now do a similar thing for PDEs on an infinite space, infinite dimensional space. And this is where Floer homology and Fourier homology were like born, because now we start doing Morse theory, this same idea, but on a functional, on an action functional. So
we can do it in infinite dimension.
Exactly.
The modular problem that we just encountered was for the instanton ones. So maybe intersecting self-dual and anti-self-dual curvatures in Yang-Mills or whatever. What is it for here? What is the modular space? Is it always like in the case that you just mentioned? No, that the is it still a modular space of flow lines?
For the Floer theory?
Yeah.
Or for Floer theory? Or, yeah, for Floer theory is no, it's more complicated. So you look at you start looking at something called stable curves, and these stable curves are solutions to some PDEs. These are called the Floer equations, and again, it's a differential operator, the solutions to some differential operator, and so this gives you like the thing, and you look at the moduli space of solutions. This gives you like the stable maps, and you want to also compare that with some action functional. That's a bit more annoying to describe, but you looking at this whole thing, it gives you the thing. I'm not exactly sure what you're looking for, but along those lines, hopefully something sticks. I'm not exactly sure what you're looking for, but something there.
Do we have any?
Do the results of this apply to just like classical non-relevant relativistic quantum theory, or is it, or would like the correction terms possibly allow for like relativistic corrections?
Okay, so these correction terms, they give you the strong Morse inequalities.
Okay.
So yeah, if you actually start looking at what these things are, you'll be able to prove the strong Morse inequalities, but it requires a lot more machinery. It's not as easy as what we did here. There is this third part of the paper is to generalize it to QFTs. So, but you will need a different set of machineries. Like your whole Hamiltonian is going to be different, and you're going to have to be a bit more careful with things.
Okay, so
but yeah, so this thing is purely classical. Like I mentioned, if you give me a QFT, I can restrict to the kernel of my momentum, and I recover this. And if I solve this problem and I find that I have different bosons than fermions, the index, like the thing is different. I'm trying to get at. Sorry, if you're strict to, what I'm trying to say is like if you're strict to p equals 0, you recover this. So this whole machinery applies, but you might have more solutions that might not be encountered at the p equals 0 subspace. So you could have like solutions that are outside of this, and you have to be more careful there.
William said, yes, it is an index because it's the Euler characteristic. for
The
the Witten
Witten
index,
index, yeah.
I believe. And yeah, that's crazy, right?
Yeah,
That's crazy.
it is. Yeah, and I've never read a Witten paper before this, so
He's a very good writer.
he is. Funnily enough, he there are some people that like manage to write complicated things in a way that make it seem easy, but not easy as in like that he knows his stuff, but easy as in like I'm reading it, I'm like, oh yeah, I understand what he's saying. Like I'm not questioning it. What he's saying is like reads like butter. I don't know. Yeah.
William also said it's the index of D plus adjoint D. That part, I'm not sure. Is that true?
If it sorry, it's the index of D plus D.
Yeah.
What is the index?
I presume he's talking about the Witten index.
Well, I get okay. I don't know if I actually have no idea about that one. I wouldn't be able to say. I have no idea.
Oh, it says I'm trying to remember exactly how this works, but this is the operator whose index is the Euler characteristic. This is okay, and this is the D plus adjoint D is the Dirac operator.
Okay, yeah, you mentioned that before, yeah.
Dirac operator when it's pseudo-Riemannian.
I see. That is that's not in my field, so I'm afraid I don't know much about that.
Yeah, it's not anything crazy. It's just your Laplacian, right? If you write it down in coordinates, you have sum of squares, right, of derivatives.
Yeah.
In pseudo-Riemannian, one of them is a minus sign. That's your time one.
Yeah.
And I think that's an elliptical operator. So Witten has a sentence apparently that says the number of generators of Cairo flavored fermions, whatever that means, doesn't matter. Some physics thing is tied to the index of an elliptical operator on a Calabi-Yau manifold, and so I presume this is what he's talking about. But I don't know. But yeah, the D plus D star. If you square, you get the Laplacian, and that's exactly what you do classically with the sum of the squares. You write it as one, something a linear combination of one derivatives, power one derivatives times another one. So you kind of square root it, and that gives you the Dirac operator.
I see.
So it's the square root of the Laplacian.
Yeah.
It's always that.
Okay.
In the Beltrami Hodge theory sense, it's easier to see.
Is it easy to see that it gives you the Euler characteristic, the index?
William's saying he's trying to remember exactly, but this is the operator whose index is the Euler characteristic. So I think, we were talking about the Witten index. What is it an index of?
Yeah.
And maybe it's the index of D plus adjoint D.
Yeah. I do not know the answer, unfortunately.
That's fair.
Yeah. I don't do much. I don't do much index theory. It's more like a tool.
Well, if I figure it out,
I'd be curious to know, yeah, because to me, like I just think of it as a trace of this. I don't.
The trace of the.
Yeah, but I'd be curious.
But that's I think it's not obvious that that's an index.
Yeah.
A genuine index. You have to rewrite it in different things just to see if it's an index.
Right.
Oh. If we don't have any questions, let's thank Francisco one more time.